Shall we start?
Okay, all right. It's time to begin our last lecture today, and the last lecture by Koenraad. And yeah, please, Koenraad.
Okay, thank you, Jong-Yoon. Okay, so this is where we left off before the break. We showed that to compute the Fermion correlation function, after we do a spin projection, it's just, again, the subleading component over the leading component in this spin matrix, but it's a first order equation. So this is really the one spin index, and this is the other spin index. Okay, so let's now study this Fermion correlation function in this extremal ADS black hole. In this object, which is very strange, this putative holographic strange metal ground state that has a non-vanishing ground state entropy, and is therefore a candidate for a strange metal. Okay. Now, before, for instance, the conductivity in this object we computed numerically, but if we study these Fermionic correlation functions, but even the conductivity itself, there was a beautiful paper in 2009 by Faulkner and collaborators who showed how to do this semi-analytically. And they did this using a standard trick from quantum mechanics. You match asymptotic solutions. And the key thing that they realized is that if you look only interested in the low frequency solutions to the equations of motion, there's an overlapping regime of applicability between the asymptotic solution from the boundary end and the asymptotic solution from the horizon end. And therefore, you can match the solutions in this overlapping region where both approximations are valid, and then get an approximation for the exact solution semi-analytically. Now, we already know what the solution looks like near the ADS boundary, right? It's this, it's what I have written right here at the bottom of this slide. So what we need to apply this trick is to know what the solution looks like near the horizon, or in this particular case of an extremal charged black hole, the near horizon, the horizon geometry is this ADS2 cross R2 geometry. So we need to find out what is the behavior of the solution near this horizon. Okay, so this is, if I take the Dirac equation for this single spinner chi1, I have already projected on this 2x2 matrix, and I now take the near horizon limit. If I just do it naively, I get this, and I change coordinates to this interesting coordinate rho, which includes the frequency here. Okay, and this then is the solution to the near horizon behavior of this chi1. Now, if I act again with rho dd rho and use the Dirac equation itself, I get a second order equation. And the interesting part is that the second order equation is almost diagonal. Okay, there's just this one off diagonal term. All right, so let's now, I'm already in the near horizon region, but within the near horizon region, which is defined by this parameter rho, I'm going to again focus on the near horizon region. Okay, in other words, the deep part of ADS2. All right, that is the region where rho is where this coordinate rho is very large. However, if I take the regime where rho is very small, that is the boundary, now not of the full space-time, but the boundary of this ADS2 region. So in other words, it's the regime where you're close to this matching point. And the key part of it, when rho is very small, is that then this off-diagonal term disappears. And I am left with a completely diagonal solution in rho. Okay, or in the bispinner chi1. And that means that essentially I can really focus on the physical fluctuation. The other fluctuation, remember, is just the conjugate momentum And I only need to worry about the fundamental fluctuation. So I can look at the lower spinor component of this equation. But the equation is the same for the upper spinor component and the lower spinor component, so it doesn't really matter. We have seen many of these equations. We know exactly how to solve it, right? In first instance, you look at the characteristic behavior in the asymptotic regime by assuming that there is a simple power law ansatz. And you can see that sort of in this regime where rho is very, very small, chi has the following behavior. There's a rho to the minus nu k and a beta to the rho plus nu k, where nu k is this funny combination of the momentum in the x direction, the mass of the fermion, and the charge of the fermion times the chemical potential squared. And then there are various other aspects of it. This rho h, remember, is the horizon size that's determined by the total charge in the system, and L is the ADS radius. Okay. So the omega dependence for this system can be restored by defining rho is omega times zeta, and now extract the omega dependence back out. So if I do that, then this chi behaves near the ADS2 boundary as follows. Here I have stated that again. Now the reason I've called this zeta is not a coincidence. This is the same zeta that we had before when we analyzed the near horizon metric of the charged ADS, the extremal charged ADS4 black hole. So zeta is the natural coordinate on ADS2 that appears in the near horizon region, right? And that means that I can think of this object, remember zeta is 0, is the ADS2 boundary. This is the diverging term, and this is therefore the leading term, and this is the subleading term. And now I can apply the ADS2 CFT1 holography. The combination of the subleading term divided by the leading term is what you could call the ADS2 Green's function in this system. Okay, now let me just call this ratio the ADS2. Then if I do a rescaling, I just rescale alpha out. The total solution can therefore be written in a very suggestive way as just an omega independent spinner times the source times the ADS2 Green's function times the subleading spinner. Okay, this is a very important point. So I hope you all get this, because now we have solved essentially the equation also in the deep interior in the ADS2 region. This is the solution in the ADS2 region. We already had the solution in the ADS4 boundary region. And as I will show in a moment, there's an overlapping region of applicability where both solutions should be valid at the same time. And then I can match the descriptions, match the solutions. So that is what I'm going to do now. This ADS2 expansion is valid in the near horizon regime. And if you're a little bit more precise, it's the regime where the distance from the horizon is less than the horizon size itself. Okay. On the other hand, the asymptotic expansion from the boundary, you also have to analyze the equation a little bit deeper, is valid when the radius r is much, much larger than the frequency. And so you see there is an overlapping regime when the frequency is less than 2 times the horizon size, right? So there's a regime where the asymptotic expansion from the boundary is valid and where the ADS2 expansion is valid. And it's only true for very, very low frequencies. Okay. So for such small omega, we can match the solutions. So we simply pick a point, right? Which is within this region and within this region. And at that point, we match the solutions and their derivatives, just like we do in ordinary quantum mechanics. And when you match solutions, derivative that uniquely determines how the one solution is related to the other solution. Now, I don't have to do that exactly, because what you know from the theory of differential equations, that each independent solution of one expansion will generically be a linear combination of the independent solutions of the other expansion, right? Generically, they don't match exactly 1-to-1. So the solution that in the asymptotic ADS4 boundary is characterized by A must be a sum of the independent ADS2 solutions with some arbitrary coefficients A plus and A minus that you can determine by this matching. In the same way, the solution that is characterized by the asymptotic ADS4 expansion B, the subleading, the normalizable solution, is a linear combination of the two ADS2 solutions, the ADS2 leading and the ADS2 leading, where again, B plus and B minus are generically determined by matching the conditions. Okay, and the only thing I do now is I substitute this abstract expression into the expression for the fermionic Green's function, which is just B divided by A. So B divided by A, expressed in terms of these ADS2 properties, is B plus times the leading ADS2 solution plus B minus times the subleading ADS2 solution divided by some other coefficient times the leading ADS2 solution times A minus times the other leading ADS2 solution. And this is an extremely powerful result, which has many, many consequences. It not only is a powerful result for the fermionic correlation functions. There was a question before the break to what extent you can read off strange metallic-like properties from bosonic response functions. And this same matching procedure works for bosonic response functions, right? So the mathematical characteristics that I'm now going to derive specifically for fermions, mathematically, they also transport to bosons or any other response functions. The key part is that in this Green's function, the full ADS4 Green's function for low frequencies, you see this ADS2 Green's function pop up, right? So in particular, right, remember this really applies for low frequencies. So I can expand, do a nice expansion around omega 0. You get that this is the following term. Now remember this GK of, I didn't put it on this slide, but it's just the power in omega with some power 2 nu k, right? So this when you expand around omega 0, you must keep this term, but you can expand the remaining coefficients in frequency. And this is a remarkable result. And it's an extremely remarkable result, and I'm now going to try to explain that, specifically in the context where I have computed this as a fermion correlation function from ADS applied to a fermionic CFT. But let me also emphasize again, this is not the fermionic CFT, this is a fermionic CFT deformed by a finite chemical potential that flowed through the RG flow to some new non-trivial IR fixed point that I have labeled a holographic strange metal. And I will now make clear why this is the correct label. So if you understand something about fermionic response functions at finite density, fermionic response functions at finite density have a very specific pole at 0 frequency. This is the quasi-particle pole. These are the excitations around the Fermi surface. If you remember what a Fermi surface is, thanks to the Pauli principle, if you have a finite density of fermions, you can only put a single fermion at each specific value of a momentum. So if I put in one fermion at 0 momentum, the next fermion must have a small amount of momentum. If I put the third fermion in with minus that momentum, I already have, again, a total net momentum 0. But this way I build up a surface in momentum space. And depending on how many fermions have, that surface then ends at some finite momentum kf. And then you have small excitations around this Fermi surface, right? But those are the fermions, and it has a very nice, beautiful pole in the Green's function precisely at k is kf and omega is 0. Since here I have focused on the expansion around omega, I'm going to see if there is a specific such pole, which Fermi liquid wisdom tells me ought to be there, at omega is 0. Well, this actually happens if this particular vanishes for a specific kf. And indeed, you find, if you do this in holography, that there is a specific value of kf for which this happens. It is hard to compute analytically, but you can show this numerically. And once I know this, I know just also on general principles that the retarded Green's function must be of the following form. There is some pole strength here. There's omega minus VFK minus KF. And there's a self-energy K minus omega. The self-energy also vanishes at the quasi-particle pole, but it has this particular property, right? And this is just general Fermi wisdom, Fermi liquid wisdom. You can find this in any condensed matter textbook. But now I can compare this fully generic Fermi liquid wisdom, which is very genetic because it just tells you that I should be able to write the Green's function in the following way. Well, here I have one function of omega k, here I have another function of omega k. It just makes the assumption that there is a peak near a specific value of k and a specific value of omega. Now I can relate this to this form that I extracted from ADS CFT calculation. And what you see is that therefore the if this pole happens here, right, the pole happens at omega is 0, so the Green's function vanishes there. That means that this self-energy is precisely this remaining term. And if you do it correctly, you have to have this a plus 1 you have to divide out. This is this ADS2 Green's function therefore plays the role of the self-energy of a fermionic excitation in this holographic strange metal state. And now I can finally justify that name. Because I'm just repeating here the previous slide from holography, we deduced that the self-energy in the system is proportional to this ADS2 Green's function. And this ADS2 Green's function is just 2 to the power nu times k. It was a complicated function, but if I'm near the Fermi surface, I replace k by kf. And this is also what I mentioned as an answer to a question earlier. This now allows me to concretely define this object as a holographic non-Fermi liquid. And like I said, for many people, a non-Fermi liquid is identical to a strange metal. A non-Fermi liquid in condensed matter is by definition an object whose self-energy does not scale as omega squared. Because a Fermi liquid is an object where the self-energy does scale as omega squared. And so here you actually see you don't just get a single type of non-Fermi liquid, you can get any type of Fermi liquid that you want. Because this new KF, I should have put it back on this slide, but let me show you again what this object looks like. It depends on the charge of the fermion, which is a number that I can dial. It depends on the mass on the fermion in units of the ADS radius, which is a number that I can dial. KF is indirectly related to these objects, so it's a non-linear function. But essentially, I can tune my nu of k to be any number at KF that I want. So it's not just that I can not get omega squared, I can get any number. I can get any number larger than 1. Well, this is not a Landau Fermi liquid, but it's still a very Fermi liquid type beast. In particular, reason is that its dispersion relation is still a beautifully linear dispersion relation at low energies. So to first sight, this will not look very different from a Landau Fermi liquid, although if you look more careful, it would. But in particular, if I choose either 2 nu kf is equal to 1, this is called a marginal Fermi liquid, which has a omega log omega as a self-energy. And this is an amazing discovery because a marginal Fermi liquid was postulated purely on phenomenological reasons as one of the explanations for the strange metal behavior in some of these exotic materials like high TC superconductors. But here it follows from a computation and it's not simply postulated. And you can even go more exotic. If 2 nu kf is less than 1, you really have a singular Fermi liquid, which doesn't even have a linear dispersion relation in the system. It has a nonlinear dispersion relation. And in fact, arguably, these are not related to quasi-particles at all, because these are objects that there is a peak in the response function, but it is so broad that it decays very rapidly. Rather than giving you complicated analytical formulas and the beautiful part of this paper from 2009 from Faulkner, Liu, McGreevy, and Iqbal, is that you can compute all these things analytically, but it's more representative to give you a pictorial representation of what these objects are. So here I have plotted the spectral function. This Green's function in general is complex. So that's this whole object here. That's a complex function because, but I'm now going to only plot the imaginary part of it. And this is directly proportional to the imaginary part in the self-energy. And here you see and graphically illustrated why you broadly have these three different classes of Fermi liquids. An ordinary Fermi liquid has a linear dispersion relation. Omega and K have just a linear slope. And it looks, and only if you would look very carefully at the width of this peak, that's precisely related to this value of 2 nu K, would you see that this is not a Landau Fermi liquid, but a more subtle beast. However, for a marginal Fermi liquid, you already see right away, you see the fact that the self-energy is much stronger at low energies, that it dies out, it has a much weirder behavior. And for a non-Fermi liquid, as I see, you barely see a particle-like excitation. It dies very quickly.
Koenraad?
Yes.
Here, what is the G? G is the green function.
G is the Green's function. G is this object right here, this whole thing.
Not curly G.
No.
So
It's
why
proportional itself to curly G, but it's curly G, the imaginary part of curly G times there are more factors in the game.
So here is not clear which is the imaginary, which part is contributing to the imaginary part. So
No. So that's why there's no equal sign here.
Yeah.
It is proportional. So if the imaginary part of curly G would be 0, which it's not, then you would not see anything here. Actually, what happens then is that there is a peak, but it's infinitely sharp, so you wouldn't resolve it. But there's a delta function peak.
So what is confusing me is that this is the bright trajectory or whatever is coming from the pole of the imaginary G, not the zeros. So if you have just omega to the 2 nu K,
So
it doesn't reveal anything about this.
There's a denominator here which I haven't written down. That gives you the pole, right? But the strength of the pole is proportional to imaginary part of sigma.
So here, what you are indicating here.
Okay.
So if nu K is, for example, 2 nu K is bigger, then in small omega, maybe this is not small omega behavior. So I see. So
no, my apologies. I should have put the denominator here as well. I will correct that in a next
right.
And then you see that essentially this is it's a Lorentzian whose width is proportional to imaginary part of sigma.
Right.
Okay.
Right.
Okay. So now, why is this super exciting? So these were computations that were done mostly in 2009. But just recently, what happens is you can try to measure this spectral function A. You can measure this with photo emission, right? This is ordinary textbook, first year quantum mechanics photo emission. You shine light onto a material and an electron is emitted. And if you very carefully measure the momentum and energy of this electron, you can deduce what the Green's function of this electron was. And one of the beautiful things that happened is that the experiments that do this have significantly increased in resolution even in the last 10 years, right? And what I want to emphasize here is that this width sigma is proportional to nu K. And one of the components that entered in this nu k was the momentum. Usually you set this to the Fermi momentum, but strictly speaking, there's a full momentum dependence in here. And the resolution of these high resolution, it's called angle resolved photo emission spectroscopy, right, is such that they can even detect this you can detect this momentum dependence, right? And here is a result that shows you that in these high, this is a result in these high TC2 cuprates, which are these strange metals, that shows you precisely this is the imaginary part of the self-energy. The double prime here means the imaginary part. It shows this beautiful power law behavior. Okay, and this is alpha is essentially what was called nu kf a moment ago. This is the common nomenclature in this system, right? And so here you see an experiment in a high TC superconductor, which has this power law behavior in the self-energy exactly as predicted in holography. And this last paper, I won't show you the details here, but even shows you that that if you look in more detail, this power is subtly momentum dependent. That is the resolution with which they are working with. We cannot yet say with certainty that this is precisely an ADS2 holographic metal, but the indication that this is close, including the momentum dependence, is just is pretty stunning. So I would ask you to keep an eye on the coming results in the experimental world, which will emphasize this more greatly. And here, by the way, you see in this actual experimental data, which is the experimental version of this theoretically predicted result. It is more of this type than of this type. Okay. Are there any questions about this point?
Are you going to talk about the linear resistivity?
No, I'm not going to talk about the linear
You're
resistivity.
not going to talk about.
So there's maybe one more interesting thing that I should say, because we had a question before the break about tuning a parameter and in going from one phase to another phase. Now, remember that this object here, alpha, is this value nu kf. It's a characteristic exponent, and normally it's set by the mass and the charge of the fermion, right? And then there's a small momentum dependence, but the predominant power is set by the mass and the charge of the fermion. So clearly, once you have set the mass and the charge of the fermion, this exponent should not change, right? But one of the curious observations that are done experimentally is that if you look at various points in these high TC superconductors for various dopings, that the value of alpha changes. And in fact, it changes from values where it's less than 1/2. So these are these very, very, very non-singular Fermi liquids. And at optimal doping, it's almost exactly 1/2. This is this marginal Fermi liquid. That is not entirely a coincidence, because people postulated this marginal Fermi liquid precisely to explain the data before, except that now it follows from a computation. But at overdoped, it becomes slightly larger than 1/2. And the only way to understand this from this ADS-CFT type of description, or even more general, from the theory of critical phenomena, where the idea is that exponents are very insensitive to the details of the system, right? So if you change the system slightly, exponents should not change. But here you see exponents change, right? And so this is a very strange feature where, as I change the doping of my high TC superconductor, the various characteristic exponents of the responses change. And so this, you shouldn't think of this as somewhat other a theory which is locally quantum critical, but there's a local quantum critical theory for this doping, and there's a slightly different local quantum critical theory for that doping, and there's a third quantum critical theory for that doping. And in fact, there's a continuous line of locally quantum critical theories in the system. This is very weird. This is completely not understood. but there's supporting data from transport measurements that something like this is happening, and it is a big mystery. But one of the things you can do is you can at least for any single one of these locally critical points, you can try to apply ADS-CFT and explain it. And of course, in ADS-CFT, it's very easy by hand to tune this exponent to whatever you want.
What is a big lambda?
This is just to make the dimensions. The dimension of this object is dimension of frequency or energy. So this is just an overall scale that you put in to make sure that this object has the right frequency.
So this is coming from the what, ADS2?
Yeah. So if you would do this very carefully in ADS2, indeed as well, it's related to it must be the only scale that sets ADS2. So it's related to mu, right? So this generically, this Green's function, all right? Here you see it. Generically, the Green's function of a fermion has dimensions of 1 over energy. So this must have dimensions of 1 over energy. Sorry, dimensions of the denominator must have dimensions of energy, right? This must have dimension of energy, and this self-energy must have dimensions of energy. Okay, and that means that whereas this object has dimensions of energy to the power 2 nu k, right? So that must mean that this object here has some dimension of 1 over energy to the power 2 nu k minus 1. And if you do this very precisely, you find it's some combination of mu, which is the chemical potential, and some other parameters.
I saw that one of your figures is for an extremely overdoped sample. Is it still, I mean, it has often been speculated that the overdoped side of the dome is pretty much a normal Fermi liquid, but recently there have been some questions about that. What does it look like in your analysis?
Yeah, so this is one of these results that seems to indicate that it's not an ordinary Landau Fermi liquid in the overdoped region. Because you see here this beautiful scaling behavior with an exponent. Well, you see it starts to approach alpha as 1 is an ordinary Fermi liquid. So it starts to approach it. The best fit is alpha as 0.84. So it gets close, but only if it would be exactly 1, right, would it be a Landau Fermi liquid.
And then this is an experimental question. Usually ARPA's experiments on high TC are done with BISCO because of the nice edge surface quality. But it seems to me, I'm just quickly reading it, it looks like you aren't using BISCO. Why did you choose to not use BISCO?
This is a BISCO. It's not the standard 2112. It's 2201.
Oh, it is BISCO. Okay.
Yeah.
Sorry.
Yeah.
Confused.
Okay.
Great.
Okay. If there are no further questions, then I'm going to now do something slightly different. Almost everything we have computed up till now are just small fluctuations. There are 2-point functions, right, around a fixed background. But life is not just all 2-point functions, right? And there's very important life that is not 2-point functions. And this relates to the holographic superconductor. What I just said was a more technical introduction, but there's of course a far deeper physics reason why we should consider this. Remember that this ADS2 object, this finite density, 0 temperature, exotic holographic strange metal, which we've now have argued based on the fermionic response functions, is really sort of what condensed matter physicists understand as a strange metal. It has this curious non-zero ground state entropy, right? Which from general thermodynamics considerations should mean that it's highly unstable. And condensed matter intuition would tell you that the main instability is towards superconductivity. Superconductivity in condensed matter language is just a spontaneous symmetry breaking of U1. And that seems not entirely strange, because remember, it's precisely the finite density, or the introduction of a U1 charge, that creates this zero ground state empty. So if some or another, you expect that the instability is in this U1 sector itself. And then the obvious instability, once you have a global current, is spontaneous symmetry breaking. So this is not a surprising intuition. But we can test this. We can test whether this is indeed true, whether there is an instability towards superconductivity. I'm not going to argue that it's the main one, but I'm definitely going to show you that there is one. Now, realizing that this is related to U1 spontaneous symmetry breaking, and recalling the fact that in the U1 theory, in the conformal field theory on the boundary, we consider this U1 as the global charge in the system, right? It's ordinary Goldstone spontaneous symmetry breaking, and I need an order parameter to understand it, right? So I need to have some object which is charged under U1 that generates a vacuum, that acquires a vacuum expectation value. And the simplest such order parameter is simply just a charged scalar field. So before I introduced a charged Dirac fermion, but now I'm going to introduce a charged scalar field, right? And I just take my standard Einstein-Maxwell theory and I add a charged scalar field to its description with an arbitrary charge Q again and an arbitrary mass m squared. Okay. Under normal circumstances, if you remember your spontaneous symmetry breaking, you need some kind of a Mexican head potential, and you need also a phi fourth term. I'm not going to introduce it here. I won't need it. Although if you very carefully study a holographic superconductor, you will also need this lambda phi to the fourth term. But for the predominant instability, for the small fluctuations in the system, it's not relevant, and so I will not introduce it at this time. Okay. Now the first thing you do, also if you would study this in ordinary field theory, spontaneous breaking, you look at stability of the system. Okay. So let's Fourier transform along the boundary directions, right, around the t and the x directions, and look at the radial equation of motion for this charged scalar field phi. Now here we have the normal Laplacian. Here we have the Fourier moments along the boundary. Here's the momentum term. And then there's the frequency, and the frequency now in the normal way is shifted by Q times the Q times the vector potential. And I've used here the fact already that I'm studying this in a charged black hole background. So I've only turned on a vector potential in the time direction. Otherwise, I would also have a plus Q AI in the K term. Okay, so I've made a small simplification here. And now I substitute in the actual background for the extremal ADS4 Reisner-Nusselt black hole. And then you get these various warp factors here in the system. And this is therefore the equation that I should study, whether this system has an instability. Now, an instability should require very little energy, right? We can concentrate on the very small omega fluctuations. And then we can perform exactly the same matching analysis as for the fermions. Remember, right, this matching analysis works for small omega for small fluctuations around the background, right? So let's, again, do the story that we started with 2 days ago. We look at the behavior near the ADS boundary, where I have the leading term as E delta minus D plus B R to the minus delta, where delta is now the object with the positive sign. Okay. And the particular aspect to look at is what happens to this square root in this system. And this tells you that this scaling dimension actually stays real for all values where m squared L squared is larger than minus 9/4. And this is pretty remarkable, because it appears that near the ADS boundary, this equation still makes sense for negative m squared. Normally, when we study an instability in a scalar field, that effectively means that I have a negative mass squared. If you remember your Mexican head potential, right? If you sit at the top of the maximum head, it's the negative quadratic curvature. The effective mass is negative on the top. That signals the instability. But here it looks like I can have a negative mass as long as it's larger than 9/9/4, and I'm still okay. Okay. So the way actually you can understand the fact that for a naive negative mass squared, everything is still okay, is that I'm not studying a scalar field in nothing. I'm studying a scalar field in ADS. And in ADS, there is this effective gravitational potential that we discussed on the first day that compensates for this. If you have a little bit of a negative mass, it still keeps the system stable. So if I have a slightly negative mass squared, I still have a stable system, or I still have a consistent system at the ADS4 boundary. Okay, so it doesn't look like I have an instability here, or at least m squared L squared is larger than -9/4. But I have to do this matching analysis, right? Because I want to study the equation at low frequency. And if I make the usual steps, I'm going to be a little bit quicker now. I'm just going to immediately write down for you what the equation for this charged scalar field is in the ADS2 region. It's this equation right here. And again, its asymptotic behavior near the ADS2 boundary can now be classified in terms of its scaling behavior in this component zeta, where this delta is the ADS2 scaling dimension with 1/2 plus nu k. And this nu k is the same nu k that we had earlier for fermions, except now it's the k for nu of k for bosons. But again, it depends on the momentum, it depends on the mass, and it depends on the charge of these of the boson that I choose. Now let's take the case where k is 0, right? And take an homogeneous insulator. Then you see that the ADS region, the scalar is unstable if this m2l squared is m2l squared, right? I'm missing a quarter here in my story. I'm sorry about that. There should be a d squared over 4 here. And larger than m squared L squared over 6 is larger than -1/4. What I'm missing is the equivalent of this 9/4 term in this expression. Okay. So a zero momentum scalar mode therefore has a mass window, right, between -6/4 and m squared L squared over 4 is 9/4, where the system has an instability near the horizon, but is well defined as a theory. I apologize for that. So what you should do here is near ADS2, the correct scaling dimension, this nu, should have this object here, and you should realize that this 9 is nothing more than the ADS, the d minus 1 squared, right? So for ADS2, this becomes a 1 squared, and that's this 1/4. And this 6 comes from the fact that it's now the m squared in units of the ADS2 radiation. So there's this small window where if the mass squared is less than -6/4, but larger than -9/4, where it's unstable in the ADS2 region, but it's stable in the ADS4 region. What this means is that the system has an instability near the horizon. That's this ADS2 instability, but it's well defined as a theory, right? As a UV, in the UV, there's no problem. And this is the instability that can trigger something interesting happen. That means under the RG flow, even if I start very well defined, as I go to lower energies, something should happen. Okay, so what should happen? I only know that there is this instability, right? But now I have to understand what happens after this instability is triggered, and how do I, where do I arrive? Now, secretly, I already know something that's going on, because I have a charged object that's unstable, right? Its initial value in the extremal ADS black hole was 0, and the instability signals that this object phi wants to now acquire a finite value. So this is what's related to sort of the spontaneous symmetry breaking in U1. So I now have to therefore study a system where a new background, where I have Einstein's equation, Maxwell equation, and the scalar equation, where I look for a solution where phi is not 0. Now I can study this whole system, but that's rather difficult. The essential physics is already captured in a simple limit where I first rescale a mu by the q of the charge of the scalar field, and also the phi field itself. And then for q is infinity, the dynamics decouples from the gravity sector. So I have this then as the Maxwell equation, with this as the source for the Maxwell equation, and this is the phi field equation of motion. But in this limit, the stress energy tensor disappears. So for the vacuum Einstein equation, I can take the ADS Schwarzschild black hole. Notice that there's now no charge. So I studied the system at finite temperature, and I studied the combined charge or electrodynamics with the charge field interaction in the background of this ADS Schwarzschild black hole. As I said, you can study the whole system, but this already captures the essential physics, because what we're trying to see, we're trying to understand whether there's a solution where phi is finite. So let's make an ansatz that will maintain the translational and the rotational invariance of the black hole. So we assume that phi is only a function of the radial direction, and we assume that the electrostatic potential is also a function of the radial direction. And then all the other components of the vector potential are 0.
Koenraad?
Yes.
Could you go back to one page? So here in the large Q, so Q is what? Coupling, right?
Q is the basically it's basically the electromagnetic coupling constant. Yes.
So what you are saying here is YQ goes to infinity. Maybe so what you are saying is electromagnetic coupling is a dominant.
Yes, that's exactly what it means. Yeah, it's exactly what it means. It means that it means that the electromagnetic force is infinitely strong. So that's the dominant physics. And then there's some, at subleading level, there's some gravitational response that happens as well, but its coupling back is not relevant to the story.
Thank you.
Yeah. Okay. So if I make this ansatz, right, then these I now ignore the Schwarzschild, and I said, well, this is the Schwarzschild solution. Then these equations reduce to actually only 2 equations, one equation for the vector potential phi, capital Phi, and one for the charge scalar field, little phi, right? And they're just these 2 equations in the system. And this is the system that I now have to study to see whether there's a non-trivial solution for this object phi. Now, before I can study this, I have 2 equations. Oh, my apologies. 2 second-order differential equations. So I need 4 boundary conditions to have a well-defined system. Okay. Now, the obvious ones are the boundary conditions to consider near the ADS boundary. I have a finite chemical potential, so that means that the electrostatic field phi should be proportional to mu, a constant. That's the chemical potential plus other stuff. Okay. But let's also think about what should happen for the scalar field. Remember, the scalar field had 2 fall-offs, had a power r d minus delta, that was the leading term, that was the source term, and had a term r to the power delta, that was the subleading term, or in other words, the response or the vacuum expectation value. Now, we're looking for a system which is naturally on its own unstable. I should not have to introduce a source. I'm looking for spontaneous symmetry breaking, right? In other words, it's not driven by the outside. So I'm trying to look for a solution where the explicit source is kept 0, and nevertheless, I have a solution phi, which is non-zero, and which by the field equation must grow as r to the delta. So this is literally, of course, encoding the physics of spontaneous symmetry breaking, right? I have a finite, I have a spontaneous creation of a vacuum expectation value, which is charged under a global symmetry. And this value O, or the VEV of O, will be the order parameter in the dual theory. So these are two of the four boundary conditions, and I need two more. I need them at the horizon. Remember, these are the objects that I have to determine the interior. Now, one is extremely simple, that because of the Maxwell equation has a gauge, is really about gauge dynamics, and the gauge consistency always requires that the vector potential vanishes at the horizon. So simply self-consistency of the Maxwell equation tells you that the gauge field must vanish at the horizon. But you can now substitute this into the scalar field equation, and then you see that the scalar field equation only makes sense at the horizon if there's this following mixed boundary condition between its derivative and the value itself. So this is the sort of, in a self-consistent requirement, we require that this is then the boundary condition at the horizon. And now I am complete. I have four boundary conditions, two at the ADS boundary, one for phi and one for capital phi, and one for little phi, and also two at the horizon, one for capital phi and one for little phi. And now I can solve this system. Okay, it is still now a coupled set of two nonlinear differential equations. That's hard to solve analytically, so you solve it numerically. And what you find for very high temperature or very small charge, right? There's no non-trivial solution. In fact, the only solution that you find is the variation on the charged black hole solution. This is, of course, fully understandable. We know that from second order phase transitions, the ones that generate spontaneous symmetry breaking, that at high temperature, you're in the disordered phase, or in the phase where there's no spontaneous symmetry breaking. It's once you lower the temperature that the Mexican head develops, and you spontaneously generate an order parameter. And indeed, if you choose the charge reasonably large, there is a critical temperature chemical potential ratio for which a non-trivial solution exists. And here you see the development of this order parameter as a function of the temperature. Once I lower the temperature below some critical temperature Tc, a vacuum expectation value for this order parameter develops. And this is the physics of spontaneous symmetry breaking. And you can now really check that this is indeed a superconductor, right? Because this is you want spontaneous symmetry breaking by computing the conductivity in the system. We've already shown you how to compute the conductivity. Again, you compute it numerically. And you see indeed that in the, if you go to the superconducting state, this curved line is the corresponding solution for the values of mu and t, where you have not in the superconducting state, but if you're in the superconducting state, you really see that there is a gap that opens up, the superconducting gap, with a very high delta function and infinite conductivity. So this really is a holographic superconductor. And what I want to emphasize here is that we've now gone beyond, right, beyond computing responses, 2-point functions, or even small 3-point functions. This is really a full, nonlinear, novel solution to the Einstein Maxwell charged scalar field, scalar dynamics, and it encodes a holographic superconductor. And you can check that this is really the right object. You can compare its free energy of the radius Rystrom-Nordstrom black hole to the superconductor, and indeed see that below Tc, it becomes the preferred solution. You can see, look at its entropy indeed decreases, and then from the entropy, you can compute the specific heat, right? These are all objects that we now know how to compute in these objects. Now, this is where my lectures end. You can now study within this holographic superconductor any other properties that you want, the susceptibility towards superconductivity, you name it. These are all 2-point functions in the system. You can look at other types of spontaneous symmetry breaking. One of the features that I have not mentioned here, and is an obvious next step, is that, remember, if I have this translationally invariant black hole, you have this delta function peak in the conductivity, which is just the fact that if I have finite density, right, I put an electric field, this object will want to accelerate forever. one of the main areas of research in the last 9-8 years is to put in some translational symmetry breaking in these holographic systems, and then you can get a finite conductivity. And this is precisely related to the question that was asked several times. One of the other very well-known characteristics of these strange metals is that the DC conductivity scales linearly with, or linearly inversely with temperature. The conductivity scales inversely and the resistivity scales linearly with temperature. And people are trying to explain that, right? So this is one of the aspects in the system, but you can do essentially many things. You can add magnetic fields to the story. As I said, that's also not so difficult because there is a dionic black hole solution, which is dionic means it has both an electric and a magnetic charge. And you can look at the responses in magnetic fields. And there's a whole world that you can explore this way. And many of these features have been explored in the last 8-9 years, but there's still much to explore. There's one thing I want to end this on, is that I want to really emphasize, because often when you talk to condensed matter physicists, either experimental or theoretical, they're often quite puzzled, and they're like, how on earth could anything like ADS-CFT, which is a large and supersymmetric Yang-Mills theory, have anything to do with real life condensed matter physics? And what I want to emphasize is that we're not interested in the large NC super Yang-Mills theory. What we have done is we have applied some deformation of this theory that triggered an RG flow, and we're studying these new emergent holographic fixed points or these new fixed points in the theory. And by the universal macroscopic of this physics, it doesn't matter where I started from. And in that sense, applied ADS-CFT really has a chance. And as I've seen, I've given you some indications of being relevant to explain some experimental research. And in some sense, this has now also been theoretically validated. It was already asked that there are now conventional condensed matter models, such as the SYK model, which also flow to the same infrared fixed point, and therefore has the same infrared dynamics of the system. And it's precisely the infrared dynamics. In fact, you can show that this SYK flows precisely to this ADS2 cross whatever type strange metallic state that you have was first discovered here in ADS-CFT. So with that, I want to thank you very much for your attention. I believe there's a second set of lectures the second week, and hopefully it will take off from this and go towards more some of these applications. And of course, I'm still, as always, available for questions. Thank you again.
Yeah, thank you very much for your very nice set of lectures.
More than welcome.
I really appreciate, and I think the student will also very much appreciate your effort. By the way, is there any experimental kind of data which shows momentum dependence of this new K?
Yeah, so I can actually show it to you if you give me 1 second. Okay. So let me share my screen one more time. Okay, so this is the actual paper. So this was the figure that I showed a moment ago. This just looks at the power law behavior of this self-energy. Okay, so how do you extract this self-energy? Well, what you do is you look at this this response function, and as I said, you look at the cross section of this, and then you very carefully measure the width. And the width of this peak is proportional to the self-energy in this way. And here you see this power alpha appear. So I can actually,
and how do we see the momentum dependence?
Yeah, that's what I'm going to come right now.
Mm.
Now, if you do this very carefully, here you see these cross sections at various different energies, right? This is at the Fermi energy. This is at 200 MeV away. This is at 300 MeV away. Okay, and here you see these very sharp peaks. You see that as you go away, the peak descends, and these are perfect Lorentzians, which means I have no momentum dependence in the power law of this fit. Now the point is, you see the data is good enough to see that a perfect Lorentzian, especially if you're a little bit away from the Fermi surface where the peaks are a little bit broader, is not a good fit. You clearly see that here it underfits, and here here the fit is below the line, and here it's above the line. And you see it in the residuals. The residuals has a clear asymmetry. Okay. And what we realized is after several tries is that if you now make that exponent momentum dependent, which is sort of the first notion that you will get from holography, you would get the following fits. So here you have a momentum dependence in the exponent. Let me see if I can show you the precise form. This is the precise form that's fitted. So we add a linear momentum dependence to this exponent.
Mm-hmm.
And then you can redo the fit, and you see that the fit is really significantly better. There's still not perfect. There's noise in it. There's still residuals, but the residuals are far more random than they were before.
Mm.
Okay. And one key part of this fit is that what you do experimentally is you actually fit a new Lorentzian for every different value of the energy. Okay. But the coefficient of this K dependence is kept fixed when I change from energy to energy to energy. So you really see that same coefficient fits very, very well. And I'm happy to have a longer discussion about this paper, but I hope that answers your question to first.
Okay, I appreciate you showing these data.
Yeah.
Another question, which is very general, is
yes.
What is can you tell me just briefly the status of linear resistivity in temperature? The people regard it as understood by holography, or
no, it's a giant mystery. So the data is rather unambiguous, beautiful data, right? But it's theoretically not understood. We have our own notion of what could explain it. I actually mentioned it briefly in the answer to one of the questions here. That if you think of this as having a hydrodynamic origin, it's directly related to the shear viscosity in the system. And if you assume that the shear viscosity has this Planckian dissipation, which means it's linear in temperature, then you get it essentially for free. But you still have to assume two things. One is that indeed it's hydrodynamically determined, and B, that Planckian dissipation applies, right? So we are literally talking with several of experimental groups if whether you can show indeed that the transport in high TC superconductors is hydrodynamic. This is still a big unknown.
I would have thought you would have said it's been answered because you answered it a few years ago. So I'm surprised that you're saying it's not explained. I mean,
no, I mean, we give a possible explanation just to show the linear in T resistivity. But this linear in T resistivity, like I said, the explanation rests on two assumptions. Okay, there's a reasonable argument to be made that this object has Planckian dissipation, also based on this precisely on the fermionic response functions and the holographic strange metal. The power law response functions, but that's an indirect evidence. But the stronger thing is that you have to prove that the transport is hydrodynamic in origin, and this is very, very different from ordinary metals. I don't know if you followed the literature on on graphene and these other. They have a name. These collective systems which have a hexagonal structure, where many of these people try to look and have indeed found that the electrons transport is governed by hydrodynamic behavior. But that's at low temperatures in a very pure regime. And for higher temperatures and away from when the impurities become large, you have ordinary sort of ballistic transport and not hydrodynamic transport in these systems. So, and for strange metals, this is still completely unknown.
So what you're saying is that essentially your explanation takes two things by fiat. You have to say these two things by fiat, and then you get your conclusion. But
yes.
And then about hydrodynamics, you mentioned that earlier, and I was surprised though the last at least today you didn't mention hydrodynamics very much, and I'm wondering, was that always behind or parallel, or everything you said could have translated into hydrodynamics, or is it just was going in a different direction? And I mean, most of you looked at solving equations close to the horizon and stuff, and matching boundary conditions and so on. Was there some parallel in hydrodynamics, or is that going in a completely different direction?
No, there's some parallel in hydrodynamics. There are some subtle issues there, which actually we are still at them ourselves resolving in this issue. You see, hydrodynamics is controlled by conserved currents, right? And let me show my slides back, because what I'm going to say now, this is an extremely good question. And an extremely important one as well.
I guess, were you secretly doing hydrodynamics this whole time, or
no,
was
no,
this...
no.
You weren't.
I want to
Okay.
emphasize precisely that this is what is the difference. Okay, so here you see my slides again.
Yep.
Okay. Okay, this is the object that I want. Where is it? Here. So I've argued, I've shown it in the context of fermionic two-point functions, that in this ADS2 strange metal state, right, the generic response function of the Green's function looks as follows, where this curly G is the ADS2 Green's function, so there's always a power law in frequency. But you do have these other parts, okay? And I've also answered in the context that this, we actually saw it in the holographic superconductor a little bit, right? That this shape of the Green's function is generic for any two-point function, as long as you compute it in this extremal ADS2 black hole background, or in other words, in the holographic strange metal. So in particular, this also applies to the response functions that you apply the Kubo relations to, right? Which gives you the transport coefficients and objects like that. Those are two-point functions in the currents in bosonic variables, right? Here we apply it to fermionic variables, but the general structure of this correlation function still always applies. So that's part one of your answer. This is the universal part. And that's also was in response to your earlier question. This is how you can sort of determine, not without resorting to the fermionic response functions, whether you are in a strange metal state or not. However, there's now comes a crucial part that a lot of people have focused only on this curly G part. And part of that is that there is a regime where it dominates the spectral function, or in other words, the imaginary part of this response. And again, many transport coefficients we've always seen are only related to the imaginary part of this response. But I can actually now appeal to precisely Sang Jin's question earlier. Even though the imaginary part of this Green's function is directly proportional to this, there is also this pole structure in the system. And that's important, for instance, here, to actually get this response out, right? The width is controlled by this, but the pole behavior is controlled by all these other coefficients. A+0, A+1, and all these other terms, okay? And in the same way that the location of the fermionic quasi-particle pole, right, is controlled by A+0 and A+1, and only its width is controlled by the ADS2 Green's function. Well, if you're in the hydrodynamic regime and computing the two-point function of conserved currents, what you are actually probing is the behavior of these A+0 and these A+1s and all that other stuff. Actually, you don't really care too much about this GK omega. So even though in that sense, the hydrodynamic regime is far less sensitive, or is not as all sensitive, well, not far less, that's the right way, to the strange metallic state than other response functions. And this has a very, this is a very deep reason. It's because hydrodynamics is related to symmetries in the system. And just based on the symmetries, you can already compute what the response functions are. And of course, the strange metal state respects these symmetries. So that has to come out. And it's only in the deviation from the part that's determined by the symmetries that you can see the ADS2 response. But that means that the predominant hydrodynamic response is actually not in this GK factor, but it's in this other sector. That's fixed by symmetries. Of course, when you study a simple fermion, it's less so, or a simple boson, which is not related to conserved current. Then these guys can be anything, right? But for a hydrodynamic current or any other conserved current, these objects are not free. They're fixed by symmetries, and that is a very crucial difference. And so in that sense, you actually already saw this, right? That's why when we computed the conductivity in the strange metal here, right? It was extremely like, I told you, it's like a textbook condensed matter physics. Not much of the strange metal came in. And that's precisely for that same reason. So I hope this answers your question, that the hydrodynamics and this ADS2 thing, when you study the hydrodynamics, you have to be careful, or you can use, that's of course how we try to explain the linear and T resistivity, that you can, the symmetries play a very important role in there. But it means that not everything is determined by this ADS2 Green's function, right?
So
put it this way, the mechanism that we have proposed for linear and T resistivity relies on the universality of hydrodynamics. And there are other people who have used holography to try to explain the linear and T resistivity, and they precisely used sort of this behavior of G of K. But that's, like I said, that's physics. The physics is extremely different. I just got an upvote there, I think.
No, that's my son, sorry. Youngest. So overall, what you're saying is that I think maybe you're saying that ADS-CFT is one way to argue for fluid dynamics, but in the end, fluid dynamics is actually just is a sort of not that sensitive to many of the details of ADS-CFT and all the wonderful things you can derive from it.
And that's essentially the power of fluid dynamics. Now, I have to say that our motivation, actually, the reason why we came up with this story was from a holographic computation. And if you read our paper, you can see it. But we realized after we did the holographic computation that the mechanism which predicted this linear and T resistivity had nothing to do with holography. It's just it was just the fact that it's exactly completely determined by hydrodynamics with one holographic input, right? That in holography you do of course have this very easily have this Planckian dissipation, which tells you how the viscosity scales with the temperature.
So
that is one extra ingredient.
But ADS-CFT does give you a way of deriving or justifying the fluid dynamics, I think. Is that right? And,
yes.
Okay. But some of the results that you had, like the special exponents and so on for your experimental analysis of the ARPAS data, probably that went beyond what you could get with fluid dynamics. So it's
Yes,
sounds
precisely. Exactly. Exactly.
okay. So you aren't all thinking of fluid dynamics. It's one of the sort of spin-offs, but could be a very powerful spin-off.
Oh, well, we've now realized that this is very important, so we're now studying it more. But yeah, and initially we were not thinking about that. No.
Okay, thank you. Thank you for everything. It's been a great series.
You're welcome.
Okay. Yeah, we have 12 minutes left. So I would like to ask, is there any question from student or other audience?
Yeah, actually, I have one just a comment about the I and my students' activity, and actually we can calculate the Fermion green function. So I mean this decay rate, and I mean by the computation, I mean if the temperature is bigger than the any mass gap present in the theory, I think that we can generally show that that conductivity or any quantity, I mean any two correlation function has the width which is proportional to temperature. But I'm not sure whether you read the paper or not. But
Maybe you can send me the paper. I'm happy to look at it.
It's a very my recent paper last year.
Okay.
I think that the title actually hide the content about this one, but it has a very short paragraph which contains just a computation of the gamma.
Yeah.
And the picture of it, both numerical and analytic. And it has a very also not only the computation, but also argument that why we should have the width, which is proportional to temperature.
Okay. I will have a look at it.
So I will appreciate if you give me just any comment.
Okay, I'll do that, Sang.
Yeah. Okay,
My
thank
pleasure.
you very much. I really appreciated your lecture.
Okay.
And I hope to see you in person again.
Yes, same here.
Mm.
I hope I have fulfilled my my task, which was to give a starting from scratch introduction to.
Yeah, it's very nicely, yes. Especially the first half is really crystal clear exposition.
So so I hope that this gives your students an easy step up to do some research computations.
Yes. Great.
I wish all of you a wonderful remainder of the school, and indeed, I also hope to see all of you, Sang-Jin, Kyung-Yoon, everybody soon in real life.
Yeah, hopefully within this year.
Yes, indeed.
Okay, great.
Okay. See you.
See you.
Okay.
Bye-bye.
So yeah, so I have to officially finish this lecture. So let's thanks Koenraad again, and let's finish today's final lecture. See you guys.